So today I wanted to expand a little bit on directions that we can take the square root of a process in order to get a little bit closer to the way Casper works. So this is not exactly the way Casper works, but it's a step in the same direction, towards that direction. So if you recall, the point about the square root of the process, or the nth root in general, the nth root of a process is that you have n different processes that, when pared together, give you the behavior of the process. So the nth root of p, when you par the nth root of p with itself n times, you get a process that is bisimilar to p. And one of the big differences between that and Casper is that Casper doesn't require that all of the processes involved behave in concert, in the same way. With respect to a particular the commit to a particular IO action. So Casper is affine in the sense that you can not have n processes for the nth root, but n or more processes for the nth root. So let me stop there and just check in and see if that makes sense. Do people understand what I'm saying?
Well, this idea of n root plus more, I guess, I don't know, that's for some reason that seems questionable to me, that something like that would be possible. But I mean, we're not breaking laws of mathematics by doing that.
No.
Okay.
So hang on a second. Let me.
So this means that in Casper, some of the nodes can stop being sync, right? This
right.
Mean
some of the nodes can be out of sync, right? Which is roughly equivalent to in Casper. You have the bulk of the weight behind one process, but not all of the weight is thrown behind one process. Does that make sense?
Yeah.
Cool. All right. So I'm just gonna screen share here. So I'm curious as to why your intuitions, Steve, would suggest that you have that's mathematically challenging.
So I guess I've just been kind of sitting here thinking about it. So this the sum of the square root plus more, and then how is more defined? More could essentially be infinite, couldn't it? But in order for that to properly equal p, we would have to have a finite bound of what more would be. It just seems like more becomes very ambiguous, and it could if it's finite, yes, I could see that then more plus the sum of the square roots equaling p. But if more becomes unbounded and infinite, then I think, wouldn't we have a problem there? Then p would be infinite as well.
Sure, but when we do replication, so first of all, I appreciate you elaborating. So that's an interesting observation. So can everyone see the equation?
Yes.
And if it's challenging in OmniGraffle to put a little superscript n right here, but so this is the square root, and if we were to have an nth root, then it would be nth root of p par nth root of p par blah 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 nth root of p, where there are n copies of that, is bisimilar to p. Now, with affine, you don't necessarily have to have all of them. You don't have to have this thing adding up to n. You know, it has to be. It could be potentially n plus 1 or n plus 2. So we're never allowing for or we're not intending for there to be infinite branching. But that said, a star in the pi calculus they use the bang, but we use the bang for output. But in a recursive process can be thought of as bisimilar to infinitely many copies of the process. So that kind of infinity is not necessarily so scary.
In this term affine, I'm not familiar with that. It almost it sounds as if it doesn't mean equal, but it means roughly equal or kind of equal. Is that correct?
It means you admit a kind of weakening. So linear means you know, on the nose. You have some kind of careful balancing of things, right? So inputs match outputs, or something like that, or linear in the sense of linear equations. You don't have any squares or higher order terms of your variables, right? So you're not making copies of x in your polynomial. X only occurs with a multiple. It doesn't occur with a power. So that's kind of the idea, is that we don't have any linear means no copies. Affine means you're allowed to have some copies. Not you know, yeah, I mean, that's basically the idea, is you're allowed to have some copying going on.
Okay.
Yeah, so it's weaker than linear.
Okay.
Can I ask you, is this similar applied to linear and affine types?
Yes.
In a
exactly.
similar way. Okay.
Exactly the same ideas.
Okay.
Yeah. Cool. So, but there is something that we can do, right? Which is that we can iterate the construction, right? So, for example, I could take the nth root of the square root of p, and if I had n copies of that, right? And if I had m copies of this one, so if I took the mth root here and the nth root here, right, then I would have potentially more copies of p, right? And in fact, if you look at the definition of the square root, right, the thing is that these really do behave just like p, with a small exception around IO. Does anyone need refreshing on the definition? Would that be helpful?
Yes. Yeah, please.
All right, here, let me go find it. 1 second. Okay, here we go. Can everyone see that?
Yes.
All right. So I give just the definition of the square root, and I leave it as an exercise to do the nth root, but it's not particularly. So here's the proposed definition, right? So obviously 0 par 0 is 0, so the square root of 0 is 0. And we do something funny here so that we avoid bound name issues, because we want to pass the square root through to the continuation. But if the continuation mentions y in a head position, like in a free position, we'll take the square root of it. So we change the variable at the same time. So that's just worth noting. And so you can see that essentially all we're ever doing is distributing the square root operation over the existing operation. So for example, with output, the square root of output p on x is just the square output the square root of p on the square root of x, and the square root of at x. Sorry, that should be star x, but well, I actually you need both of them. So this is the operation on name. So the square root of at x is the square add to the square root of x. But the one place that you have a problem is with par. Now, if the free names of p don't intersect the free names of q, so if they are isolated from each other, that's what this notation means. Then it is safe to distribute the operation, right? Because they don't interact. So there's no problem with just going ahead and taking this square root. Because if you were to square it, you'd have square root of p par the square root of q par the square root of p par the square root of q, right? And then because par is commutative, I get the square root of p par the square root of p par the square root of q par the square root of q, right? But the square root of p par the square root of p is bisimilar to p, and the square root of q par the square root of q is bisimilar to q, right? So we get that this thing squared is bisimilar to p par q. So that's all fine and good. That does the right thing. But if they do interact, we have a problem, right? And the problem is, what in particular, what happens if there's a race, right? So you have x, you have a process that's listening on x in par with the output, two different outputs on x. So then if we follow the definition, we'll push the square root through on all three processes. Now, if we try to square this, right, then look what happens, right? So we get a copy of this in par with a copy of this. So one way that this could evolve is that this one goes with that one. So Q1 goes this way, but Q2 goes that way, right? So that would end up not being bisimilar to P, right? Is that clear to everyone?
When you do this transformation of left to right side,
mm-hmm.
so you're basically duplicating all of the.
No, we're not duplicating. We're checking. No, when we do this transformation, right? This is the transformation. But now we want to check that if I square this thing, right?
Oh, I see. Mm-hmm.
Right. So if I put it in par with itself, that I'm going to get back the original process. So that's this in par with itself. Do I get back this thing that's on the inside of the square root prior to taking the square root? And that's where things fall down.
Okay.
Right. So what we have to do is we have to introduce an additional coordination constraint, right? So, and it's got to be the case that since when we square it, we need to get back this, that C, par C must make a choice for both copies. You see, right? So what we're going to do is we're going to write down that I've got an additional coordination constraint that's forcing the two copies to do the right thing, right? To make sure that they both make the same choice with respect to the race. And it's got to be the case that it's C par C that does that job, because what I'm going to do is if this is the square root, then if this thing is the square root, then when I square this thing, in other words, when I put it in par with itself, I'm going to get two copies of C, right? That'll be in par. So this is the thing that must make the choice for both of the copies of this thing. Is that clear?
Yes. So as you continue to square and the equation grows, C multiplies as well, keeping the constraint on the equation.
That's right. So when I square this, I'll have all of this par all of this. And then, so basically if I just use the commutativity of par, I can get this par C par C. So that's the sort of equational way to see that this is in fact the thing that must make the choice for both copies. Okay, so I'm not sure why these little extraneous marks are in here, but I have to clean those up. But anyway, so now we can just define C. It's obvious what C has to be. Oh yeah, sorry, it's left and right. It's left and right. Yes, that's right. Sorry. Now I see what's going on. What we're going to do is we're going to decorate this thing with an in left. So if you're thinking about Scala types, this is literally in lefting this thing. So all of the stuff here, and you can look at if you can look at the original row paper for what definitions for left and right might be, but just think about it as tagging. So we're going to tag this one as left and this one as right, and it doesn't matter which one we tag. So this is without loss of generality, right? So we've shoved one of these things into a separate namespace from the other one. Is that clear?
Yes.
Okay. All right. So now when so what we'll do with C is C will listen for Q1 on the left namespace and for Q2 on the right namespace. And out is going to be some channel that's distinct from everything else. So we can choose it to be, for example, this one, which is guaranteed to be distinct from all the channels that we might muck about with. But we know because of the way row works that I can always construct a channel out, which has the property that it's fresh from every local name. Again, I refer you to the row paper for that property.
Can we just say new out?
Yes. So I don't have new in this calculus.
Oh, okay.
Right.
I see.
So then the and new is fresh for all time, and out is just locally fresh. Okay, so here Q1 listens on the left side of the namespace, and Q2 is going to receive the data from the right side of the namespace, and then out is going to flip a coin, right? This is a coin flip, right? So we're either going to get 0 or 1, and remember that there are going to be 2 copies of this out because we have C par C, right? So we're going to run this whole thing in par with itself. So what will happen is there's going to be 2 copies of the left-hand side and 2 copies of the right-hand side, right? Because we have this whole thing in par with itself. So I'll have 2 lefts and 2 rights. So one of the C's will grab one of the lefts and one of the rights, and the other copy of C will grab the other copy of left and the other copy of right. Is that clear?
Yeah, I'm following.
Okay, coolio. All right, so then, so now because they both grabbed that, they're both blocked on 2 outs, right? So both of them can immediately get through this gate, grabbing 1 left and 1 right. And because they both got through, that means we have out, par, out, right?
Mm-hmm.
Right, which means that it could be out of 0, par out of 0. it could be out of 1 par out of 0. It could be out of 0 par out of 1, or it could be out of 1 par out of 1, because this is a random number. Okay, so now, so we know all of the possible cases, right? We're going to grab 2 copies, right? And there's only 2 copies. So this is a locking mechanism. Is that clear? There's only 2 copies of out, not 4 copies, only 2, because there's only 2. One of these bodies is going to grab both of them, and the other one is going to be locked waiting. Does that make sense?
I'm not clear. How do you go from 4 down to 2? You
Remember,
just choose to do that?
No. Look, so I have C par C. So C is going to have, is going to encounter 2 copies of left and 2 copies of right.
Oh, okay.
Right? So both of them will grab a copy of a left and a copy of a right.
Okay.
Right? But then once they get past this, there's only 1 out. So each copy of C only does out once.
Okay. So yeah, everything. So the reducing down from 2 to 1.
That's correct. But there's 2 copies of C. So there'll be 2 total copies of out lying around. Right? And then, but the continuation, this thing which is running in parallel with this out, there on both C's, is going to grab 2 copies of out, but there's only 2 outs available. There's not 4 outs available.
Okay, no follow.
All right. Okay. So because of that, one of them will grab both, and the other is stuck waiting.
Okay.
And now we just case it, right? Right. So we go, if I get, so it's called beast and freak, right? So a freak has a head and a head, or a tail and a tail, and a beast has a head and a tail, or a head and a tail. Right. So and you just look at it. So in the case that you get in the freak case, it doesn't matter which one you pick, right? Whether you assign freak to Q1 or beast to Q1, or beast to Q1 and freak to Q2, right? That doesn't matter. So here, this is again without loss of generality. So we in the case, I'll just take one of these cases. So in the case of 0, 0, right? I get X. I'm outputting X on I'm outputting Q1 on X, and in the case of and that's what will happen is, so this thing is listening on X, these things are outputting on X left and X right. So these things are gobbling up what should go to X and making a decision about what to hand over to this process, right? So on X, we'll do the Q1, and then we'll do out, out. So the other copy will come in here. It gets both out. It sees it's 0, 0, right? So it'll also do Q1. So both copies will do Q1. In the other freak case, they'll both do Q1. In the beast case, they'll both do Q2. So clearly, when we square this thing, this will now behave just like P does. Does that make sense?
So can we say that we somehow sequentialize this first com event so that we can see the result and then do the same for another
It's
one?
not really sequentialized. It's just that we have a listener. We have something that's listening in and observing the choice, something that is listening in and forces a choice for both of them. And that's very much the way Casper works, right?
I mean, sequentialized in a sense that we need to wait the first choice.
Yeah, it doesn't matter. Again, it doesn't matter which one goes first, right? Mm-hmm. So it's not really sequential in that sense. Mm-hmm. We don't care which one goes first. And if you think about it, this is very much like Casper, right? This thing is a kind of vote. All right, so
we're using this random 0 and 1. These are the labels that we are using, right? They're like we can use whatever we want for that.
sure, it's just in the case of the square root, you have, you know, you have these cases that you have to consider, right? In case of the nth root, you have, you know, you have n squared, right? You have 2 goes to 4, right? You'll have n squared cases that you have to sort out. Does that make sense?
Yeah. I'm seeing like this can be useful in many situations.
Yeah, of course. Yeah, absolutely. So, but now, so now that we understand how the square root works, we can go back to here. All right. So what I could do is take the mth root of this one and then take the nth root of this one. So now I have m copies of the square root and n copies of the square root. Does that make sense?
This means that you have square root of square root when you
I have the mth root of the square root, and I have the nth root of the square root. Yes.
Okay.
So I'm iterating the process. So now you see, I no longer have exactly n processes. I have m plus n copies. You see what I'm doing here?
I understand what you're saying, but I'm still trying to somehow make some picture in my head.
Sure. So essentially what I can do is, so I'll just do it for the square root, right? So I'll square this one and leave this one alone. Okay, so now I have 3 copies. You see? And these really are copies of P, right? That was the point of going over this, right? The vast majority of the construction is just pushing the square root through. The only time we don't is if P and Q possibly have some interaction. Okay, so in that case, that's where you have to worry about things just a little bit. So here, these really are in different. It's 3 different copies of P, as opposed to just taking the third root of P. So these are not quite right. And so now you can start to imagine how this might be related to stake. So if we have the stake adds up to 100%, then we have the 100th root of P. But you have, for each stake amount, you do you do it so that it adds up to 100, right? So you'll take the staked root of P par the staked root of P par, right? And so that it will add up to the total stake, right? And that will begin to get you something that's very similar to Casper. Is that making sense?
I'm thinking about this square root of P.
Okay.
This square root of P in par with square root of P. Together, if we just square it, we will get square root of P with par square root of P.
That's right, which was B back to P, which is our goal.
And in this way, I'm not completely sure how. We don't need like the full stake, or we don't need to care about the total stake, right? Of P.
What you want to do is you want to relate the number of copies of a given staked validator to how much stake it is.
I see.
You can do it in terms of percentages. You can say what the percentage of the total stake that validator is staked with, and you do that many copies.
I see. And we can create as many copies that we like.
Exactly.
For some specific.
That's exactly right.
Okay.
So again, this is not yet Casper, but it's on the way to Casper, right? We're starting to relax this strictly linear approach just by iterating the square root construction. Does that make sense? So and again, the point is that I can do the kind of reasoning I can do, like, you know, just to look at it, right? To prove that this expression is going to be P, right? Well, I know that, just as you said, oh, come on, fingers, that thing is bisimilar. So that thing is bisimilar to this thing, which is bisimilar to P, right? This is the kind of reasoning I can do to get back to, well, I made a construction that I know is going to iterate, that when I go through the equational reasoning, I'm going to get back to P. So just to relate this now to how our chain works, just so that we're super clear about this. P is a smart contract. The validators are all running copies of P. C is Casper. C plus the decorations on the square roots of the processes, right? The left and the right are is Casper. Does that make sense?
Yeah, so Casper's the coordinating component that makes things attach in the order that they need to be attached.
That's correct. That's exactly right. And now what we've done is to relate that, right, through this mechanism, through the iterated square root, to staking. And but we've also sort of implicitly defined what correctness for Casper means. The correctness for Casper is that some number of copies of P is going to be bisimilar to P for all smart contracts. Is that making sense?
Yes. We don't need a total stake, right?
Yeah, but again, it's sort of staking is an extra thing, right? The main point is that when we are talking about Casper, how do we know that Casper is correct? Well, what does Casper do? It takes P and it runs several copies over several validators. And however many copies are run over the validator population, that big par has got to be bisimilar to P. That's the correctness criteria, right? We haven't up to this point, you will not find in any spec for Casper, certainly not in Vlad's paper, what does it mean for Casper to be correct for a smart contracting language? Does that make sense?
What was the logic behind? So how does, so in these calculations, you're assuming that you have the knowledge of execution of smart contract on all validators, and how would so for example, if we have these implemented in POS contract and some validator runs these calculations to get a sense if this calculation is safe and acknowledgeable.
Yeah. First of all, they're not going to run this process, right? This process, as you'll note, this is well defined, right? So it's statically defined. Whenever you give me a smart contract, another way of saying it is, if you hand me a smart contract, I'm going to look at its shape. If you hand me the smart contract 0, I'm going to hand you back the smart contract 0. If you hand me a smart contract that is essentially a 4 comprehension, I'm going to hand you back this 4 comprehension. If you hand me back an output, I'm going to hand you back this, and so on and so forth, right? If you hand me a race, I'm going to hand you back this kind of decorated smart contract, right? And so since that's what Casper is doing. This notion of Casper is slightly different than the one we've got, right? So again, I'm slowly going just from a basic row calculus, simple-minded approach to a leaderless distributed consensus mechanism. And what I've been talking about here is to relate the number of copies to the stake, so that staking can be in other words, to make there's no economics in this. That's another way to say it. This definition has 0 economics, and this definition is starting to move towards economics. Is that making sense?
Yeah, I mean, basically this last set of equations will tell us, or could tell us, how much stake is needed for the thing to be safe, for things along those lines, right? Is that what you're saying?
No, but that's an interesting idea. No, what I'm saying is, think about every copy as like a kind of vote.
Mm-hmm.
Right. So the copies are all voting, and the stake is correlated to votes. And what we're doing here is just writing down that if we were to do it that way, that it would be correct. Right. So this is not like this is not like the safety oracle. It's not like those kinds of things. This is, as you can see, this is many times faster than the Casper we've got. You can see that, right?
I see. Mm-hmm.
So Nut Zipper, do you understand what I'm saying? This is much faster than the Casper we've got.
Well, sure, much more to understand here. So you're saying that this Casper actually modifies the code of a contract. If you have a race, it will add some stuff to the execution.
Yeah.
And we'll pick a race winner.
Yep.
And here, basically, what happens is that all the nodes will pick the same winner. Is that the?
That's correct. All of the simultaneously running copies of the contract will pick the same winner.
So we are kind of don't have we don't have validators to agree like explicitly from outside, because all of them should run the same stuff.
They'll all
They
run
should-
exactly the same smart contracts which have been slightly decorated.
Oh, that's nice. Yeah. Now it's no. Thanks.
Yeah. No, it's go ahead.
I'm thinking that we somehow, when we producing this C, we are somehow we are not choosing, right? We are not choosing the branch that will be executed. We are just saying,
yeah,
we are more specific about branching. We are saying, right?
Yeah.
Is this correct?
All we're doing is, we're sort of randomly generating. We're flipping a coin or rolling an insided die, right? And
all of the validators should create the same. Should choose the same random.
Nope, don't have to. Nope, they don't have to pick the same random number.
But the matching case should be the same, right?
Their matching cases have to be the same, but the random numbers they output doesn't matter.
Oh, I see. So whatever they choose, they know.
Yeah, that was the point. So now to complete the picture, right? You can relate the random number to the total amount of stake. So you weight the random distribution to the stake, which means that the validator that has the most stake gets to pick more often the winner of the race. Does that make sense?
When you say most often, why not always?
Because you might get a plurality.
Oh, I see. So if all validators are different, then the one with the most stake will always choose.
Sure.
Okay. Understood.
Right. So now we've started to put in both the economics as well as the correctness. Right? Does this make sense? So the economics is now correlated to, which is what it is correlated to in our Casper today. The economics is correlated to the influence on the execution paths, right? That's what staking does today. The more stake you've got, the more say you have in who is the winner of the races.
It's still not quite clear to me how. So now Casper is sort of, we're picking the fork chase tips, which is the longest chain that we're going to build on. So how this is related to, so when we merge states, we have several possible futures, and we pick one of them, and we merge them if they're mergeable. So how this relates to what we're doing now?
Okay, so essentially, this case match is determining what goes in the block. This is, imagine that, so now at this point, we know precisely which COM event has happened, right? As soon as we see this match, we know the COM event that has happened. And because we know that's happened, we can record that to a block.
Yes, but if we have several branches competing,
that's the point, is they won't compete. This is the one that the only competition you ever have is on row calculus expressions.
Oh, you mean we won't have conflicts at all?
You won't ever have any block conflicts because nobody ever packages things up in blocks. They just do deploys. We decorate the deploys, and then we know which COM events to record for history's sake. These are the transactions.
But what if two validators created a blocks with conflicting transactions? They can't
Again,
do that.
they're not packaging blocks anymore. There's no blocks. There's just a you see.
How do they exchange their work?
It's all through communication, right? The way all the validators do is they act. The validators are essentially running copies of C. That's all they ever do.
Oh, okay. So it means that communication will be much smaller.
Yes. So in other words, all the processes communicate with each other directly.
Nice. So they're basically putting some tags and they're saying, let's vote. And
pretty much, yeah.
And they're collecting it. Yeah, they know the result. Nice.
Yeah, I mean, basically, the reason for variability and repeating the whole thing is reduced or eliminated here, right? I mean,
yes.
Because they're all doing the same thing. I mean, we're ensuring that they all do.
We're ensuring that they all do the same thing. That's correct.
Basically, there's no leader who will execute deploy, another will verify. So everybody just
runs.
So they run. It's like at the same time. They don't necessarily need to know anything about other. The only thing that they need is the bonds map.
That's correct.
I see.
Now, when one node says this is the answer, we record. Then what happens to the other nodes? Do they just complete their calculations and verify, or they don't?
No, they all have to complete, right? They're all running. So in the case of two, they're all running this program.
Right.
Right. And so let's say that here they don't just do this output, which will then trigger this input here, right? They also at the same time they record to a local copy of the transaction log, that transaction. Right? So now they can have a local copy, and they're guaranteed, like the other C will also, it must per force take this case, right? You can see that because you're doing out of 0, out of 0, 0. So the other copy is going to get, 0, 0. So it will come back in on this case. And so if in this case, in addition to doing this output, we log the transaction, which is that particular COM event, then we know for a fact that the local log on one C will be exactly the same as the log on the other C. Does that make sense?
And do we still need to exchange these logs, or we just
nope?
Nope. So this is a proof of execution that yes. Each validator has.
Yeah, and in fact, the proof happens before we ever run anything, right? The proof happens, in our discussion. This is the proof. The proof happens once and for all.
So it's algebraic. So
algebraic, correct.
Yeah. It's like algebraic enforcement is basically what it is.
Yeah.
Right.
I see.
Now, again, there's all kinds of ways this could go wrong, right? The one thing that this would get, that this relies on, is that messages are not lost. So if the network drops any of the messages that are critical to this protocol, then you have a problem.
And the delays?
And which
Same thing.
So here the delays are only on message sends, but yeah, exactly.
And which are messages in this case? Just to
Messages are outputs. Any output is a message.
So output of this particular code. So not all COM events that are happening on the node, but this C output from the C.
All messages are. Sure. If you can divide it up that way, so you can say that C to C communication are the ones that are like this. But if there's no if the channel does not interact with C, it can be done locally. So all COM events that don't get decorated this way can be done entirely locally. And you'll be guaranteed that both copies of the local things do the same thing. And all COM events where they are decorated, they're passed along through the C mechanism.
But how do we make sure that other peers are not cheating? So where is the state hash that we computing? If we don't have blocks, what are we verifying?
Yeah, so you just have a transaction log. So yeah, that's the other thing, is like if you have malicious implementations of Cs, then you have a problem. But the one thing to do, so one thing you can do, and it's going to be the same for all versions of Casper, right? If you have malicious validators, you have to defend against that. But one thing you can do is you can ask at any point that you type check the C, right? So the whole point of this algorithm here, and I gave a talk about that with Christian at one point, is that we can actually lift this up to the type level, right? And so we can always type check the outputs of the algorithm before we run against it. Now that's a little tricky because they could do all of that and then run a malicious version, right? And so what you have to do is you have to spot check, right? And so
how about anytime there is a deviation or variance, why don't we then say, okay, let's check? Does that work that way? I mean, basically you check when there's a problem to say who is right.
Yeah, so there are all kinds of attack vectors, right? So I'm not saying that this is the final production version of Casper. What I'm saying is this is a promising direction of research that makes a lot of headway on certain kinds of things, right? So in particular, what I've been trying to get across for quite some time is, oops, wrong. We want a correctness criteria for Casper. I argue that the most compelling correctness criteria for Casper is that when the validators smear out copies of P, and when they're all run in parallel, that's bisimilar to P. That's the correctness criteria. And if you adopt that correctness criteria, then you can avail yourself of equational reasoning. Does that make sense? So you can do the correctness for your validator code once and for all, which would be equivalent to a type check of the validator code. Now, there are lots and lots of you know, attack vectors that you have to consider. But I'm just trying to be suggestive that this is a very promising line of research. Right? We can.
And I wonder if the network robustness can be made somehow. I mean, you could probably expand this model by including network robustness as one of the pieces in here. I don't know.
Well, in this model, the error correcting code approach is directly applicable. You can directly use the error correcting code algorithms on this approach to guarantee robustness against certain kinds of message loss and delays. So that's the part that I haven't mentioned until today, but you can take those papers, which are a decade old now, more than a decade old, and you can apply them directly to this model. So you can get a solution for a wide variety of network delays and message loss. So that those two algorithms composed is what I'm saying. You can compose those two algorithms, and maybe I'll talk about that sometime. But it still doesn't address what happens if you have a malicious validator. So malicious validation is it's another attack vector that has to be dealt with seriously. So, but anyway, now you've got to go ahead.
I just want to ask, I'm thinking about cases where we don't have COM event. This basically just means if we have some send, each validator will add send to the tuple space. So
that's
there is
correct.
no.
That's right. And the same with the inputs.
Mm-hmm. And what you are saying now with malicious validator, this malicious validator can change the value of the send. And
for example, they could say the send is on a slightly different channel. They could change the value of the send. They can do the same for the inputs, right? They could swap out a continuation and those kinds of things.
I see. So only when we have a COM event, we basically just need additional C to talk about all of the branches. And
that's correct.
With that, we can have agreement. Yeah,
that's exactly right. Yeah.
This is the answer for Josh because he asked, can we package up deploy, only deploy, not the whole block? And this is even better. We can only one term we can send between validators, not even the whole deploy.
Correct.
Right.
Yeah, that's correct. Yeah. So there's lots and lots and lots of fruit to be born here. If we have the time, I mean, part of the reason I keep, sort of pointing out this work is because if we can carve out the time, I believe that our ability to optimize what we're doing is, much, much, much deeper than we have considered yet. So.
Yeah, I mean, this is actually one of the things Stanislav was asking for, is for you to articulate the appropriate abstractions of each of the parts of the R-Chain platform, so that when we refactor, we're doing refactoring in the context of that those abstractions, rather than
Sure. I mean, they're articulated in the paper from last December, not this past December, but the one before, right? So the major architectural components are articulated. But we can go into that later. Anyway, we've got stand up, so I'll see everyone over there.
Yep.
Thanks.
Thanks.
See you.
Thanks.
See you.